All right, so it says here determining the, in brackets, molecular formula of a hydrate. So hydrates are a weird sort of ionic compound. So really the word molecule, again, we're trying not to use that to represent ionic compounds. So when you have a hydrate, which we've kind of already talked about, you have this ionic compound part, but then you also have water. So water is a molecule connected to an ionic compound. And yesterday when we talked about empirical formula, that it was the most simplest, and then molecular formula was actually how many atoms. Because this is actually how many waters are in there, water's a molecule, sometimes you'll see it either way. Either the formula of a hydrate or the molecular formula of a hydrate, it's the same thing, okay? So and again, try to think of the words the same way that we use them. If I asked you to hydrate yourselves, what would you do? You would drink water. So these ionic compounds have drank water, or the water is attached to them. There is no way to predict this without having empirical data. So you're going to see that you're going to be given gram amounts similar to empirical formula. You guys did both. You did percentage, and then in the back when you did the lab, you guys used actual gram amounts, right? So you can't crisscross this to figure out how many waters. We need data, okay? And when you have something that, if it says anhydrous, that means without water. So like antacid, AN, means without acid. Anaerobic, if you're a biologist, without oxygen, versus aerobic, which is with oxygen. So that AN prefix means no, so no water, okay? And so if you want, we can review how to find the molar mass or molecular weight of a hydrate. So again, you want to add the water weight or mass to this ionic compound. And today I'm going to do it because maybe now you know that this is 18. Or maybe you can do it in your head. Hydrogen is 1, oxygen is perfectly 16, 16 plus 2 is 18. But you can still do it like 4 H's and 2 O's, whatever, it doesn't matter. But the big point is that water makes the molecule heavier. It gives it different properties. Certainly color is easy to see. So we do this topic last in chapter 6 because there's a lot of things you can do here. So if you look at the worksheet, there are different types of questions. There are questions like in your note where there might be an X here, like an unknown. How many water molecules are there? We'll look at how to find that. You can also find the percent composition that is water, or sometimes it's called mass percent of water. So you would have to do this just like you would with normal percent composition, and then put the water on top instead of an element by itself. So this is just a little bit different. But so on the next slide, it says we're going to use a modified empirical formula chart. So normally you have however many elements, right? And then you have moles or mass. This is usually given. This is from the periodic table. So we did a lesson on this. You guys did the lab for this, right? Whether you use the mass as percentages or given gram amounts, it doesn't matter. And then the mole ratio, you divide the moles by the smallest. We're going to do the same thing today, except the two columns, there will only ever be two. The second column, because normally when you have a hydrate, we write the water last, okay? So the second column will always be water. So that's why, you might have the molecular weight of water memorized because it's always going to be 18. So we're going to try to find how many waters there are versus how many anhydrous compounds there are. So when you do this, it's not really an element. So if you want to lightly cross that out, that's how we're modifying this. There will only ever be two columns. One of them is always water, and then the other one is whatever the formula is, and you'll be given it. So the example we just did, it would be like, so you know what the anhydrous is, we're going to find how many waters. This is just an example, sorry. So you'll be given the anhydrous formula to find the molecular weight. You don't have to worry about doing like a crisscross rule and stuff like that. And water is always water, but again, if you have a brain fart and you're like, I forget what water is, the question will look like this. And this is like our unknown. We commonly use X, right? So how many waters are there? So instead of finding how many elements there are separately, now we're doing how many anhydrous molecules are there, or formula units, and how many molecules of water. Also, when you do this, like on a paper and pencil task, if we were really going to do it in the lab, then maybe things always can be a little bit hairy back there. However, when you do this, the anhydrous should always be 1. So this will always be the smallest mole amount, and then the water will be greater than 1. So you can kind of check, oh, I did this right, I didn't do this right, whatever. Okay, so we can basically do an example because really all this math we've already done before, okay? So we are going to find the percent mass of water in the sample, and we are going to determine the number of water molecules, or we're gonna find X. Similar to empirical formula yesterday, you have to make sure, like, don't do the chart, don't do all the work, and then forget to write, therefore the formula is, okay? So make sure you state what the formula is. In the worksheet, I took the questions from different sources, and the questions were all kind of worded maybe a tiny weeny bit differently, and I was like, you know what, I don't mind this. So some of them will say, find the value of X. Some of them say, determine the molecular formula. Basically, that's the same thing, just worded a little bit differently, okay? To give you guys an opportunity to see how the other questions work. So sometimes, and they kind of go, well, I think I even wrote tough. They go in order of toughness. So the first ones, if you have the number of waters, then you could be asked to do A, and then you just use molecular weights. Here, just like with percent composition before, here we don't know how many waters. However, we're given an actual gram amount, so we can use those numbers. So similar to percent composition, it could be either percentages, molecular weights, or gram amounts, okay? So a 50-gram sample of barium hydroxide and then it says the formula. Again, you don't have to do that. Sometimes it might even say a 50-gram sample of a hydrate. So what that means is we know the gram amount of the hydrate. We don't know how much of those grams are water, okay? Contains 27.7 grams of just barium hydroxide. Again, it might say anhydrous. Here I've given you the formula without water that implies anhydrous. So the questions could be worded a little bit different. Calculate the mass percent of water. So we know how much the hydrate is, we know how much the anhydrous is. You can't create matter from nothing, so the difference between them is the gram amount of water. Let's say you have a brain fart and you subtract the wrong way and you get a negative number. Can you have negative grams of water? No. So it just means you've subtracted wrong. So always do basically what you're given, the biggest minus the smallest. It's actually pretty straightforward. So just like with any percentage, it's always the part over the whole. You just have to remember the whole compound includes the water, the hydrate, not the anhydrous. So you guys have this whole space to do. I'm going to make a new slide, but you guys can just keep going, right? You got lots of room there. Okay, so now for part B. We're going to make our chart. So when we are finding the formula, you do mass, molar mass, moles, mole ratio. It just depends. Are we doing elements separately? Are you doing the ionic compound and the water? As soon as it says hydrate, or the question will even look weird like this, like how many waters are there? That's when you do one column for water, always, and then the other column will be the ionic compound. In our case, it is barium hydroxide. So again, maybe you are good at molecular weight or molar mass and you don't want to show your work. That's totally fine. Maybe you've made your chart big enough to show it in there. Maybe you like to show your work at the side. Whatever you want to do, okay? I'll just put it over here. That's just hydrogen. Even if you used one, it would be okay. But like I said, at this point, writing it in here is good enough. Okay, if you're good at it or whatever, you know what you're doing, and you just want to write the final answer, that's fine. Bless you. Okay, so one of the advantages of the chart, now we're going to do moles, mass divided by this. So this over this gives you this. So we're doing what we did yesterday. We're going to divide all the moles by the smallest mole amount. But we only have two columns, salt, water. The smallest mole amount should always be this, not the water. Okay? This should give you 1. So these questions are a little bit easier, really, to kind of check, did I do this right? that should give you 1, okay? Okay, so it's like 7.78, not like basically 8. Usually with these, you don't have to worry about that 0.5 thing. Usually it's very obvious what it's supposed to be. And then remember just to make sure that you have your final sentence. So really, we're just filling in the X. Okay, so this is up here. It says it's got an X. So you're just going to put the number in where the X is. So there's a lot of information in the question that can help you, okay? If you don't know what barium hydroxide is, it's in the question. If you forget what a hydrate looks like with the dot or whatever, it'll be in the question, okay? All right, so not too bad, but let's do, so if you could get the lab sheet, the yellow one out, please. We'll do that part of it together. Max, I don't know, you might have to go to the back and get it. Did anybody else not pick it up? Did you, Logan? You were here, right? Yeah. Okay, so the little half sheet is homework questions. So if you would rather tune me out, that's totally fine. When you go to the, it goes in order. So empirical formula, here's the formula hydrate. It says video of hydrate experiment because eventually there will be, what's it called? A video for the lesson, okay? So what we're gonna do, I'll try to pause it. So it's gonna show the video. Again, I did this for lockdown. Obviously, the kids at home couldn't burn copper sulfate, right? And so what we're gonna do, you're gonna watch the person do the lab, basically. So they're gonna change the blue stone into white. It'll talk about, what color is the hydrated CuSO4? You'll see it in a second. And it will, like the questions, why do you have to be careful when heating the hydrate? The person in the video will say the answer, okay? Why does the hydrate stick to the stirring rod? The person in the video will give the answer. It asks you to draw the setup. So once they get everything set up, I'll sort of pause it and give you a chance. I am no artist. You don't need to be an artist, okay? And then I like this video, again, when we were in lockdown because it actually shows the scale, but the data is in the chart for you, okay? And then the back page, you don't really need the video for anymore, okay? So it's up to you if you want to do the homework first or you want to work on the lab. What we'll do is, I would like to do, Stoic's a big lesson, so maybe after break we can do the first part of it and then after lunch we'll finish it off. So then once this is done, which is literally like 5 minutes, then you guys can choose to do this work or if you need help from yesterday or whatever, okay? It'll be a bit of a work period until 10:35 and then we'll start Stoic after. Does that seem okay? All right. Let me just... Or if you need me to pause it, yell at me, okay? Hold on, I think I have it on 2 times speed. Oh no, normal. Okay. That's already on your sheet, okay? Already on there. I think she just said it there, right? So instead of driving off the water, you can decompose the copper sulfate. If you don't heat it evenly. And then you can see the color there. Okay? So the next question says, why does the hydrate stick to the stirring rod when heating begins? So watch for a stirring rod, okay? Does anybody want me to go back? Did you guys get it? So in the end, what you're trying to do is get, similar to what you guys did yesterday with the magnesium oxide, you're trying to get as much of the white anhydrous copper sulfate in the crucible. So if it's wet and sticking to the stirring rod, then you're not weighing that mass, right? So then that can be an error. So the water doesn't evaporate. It's like, because water needs to evaporate at 100 degrees Celsius, which is pretty high. So then it makes the copper sulfate, like the liquid water, is making it a little bit wet. Wet things are sticky. Don't worry about that. Okay, so this isn't really the mass I gave you, so it does ask you about errors, so then that could kind of be one of your errors. What I'm going to do, we don't really need the video anymore. What I'm going to do is I'm going to back it up to a spot where it's got a good shot of the apparatus. Oh, there we go. Maybe. Just going to move her hand. Okay, so there's a retort stand, crucible, ring clamp, clay triangle, kind of like what you guys did yesterday, Bunsen burner. But again, oh, okay. Oh, she's not here actually. No, sorry, Anna. So again, I'm not an artist. So really, most of it is basically what you did yesterday. Retort stand, Bunsen burner, clay triangle, ring clamp, crucible. Okay, so draw that in there. Oh, it even says, doesn't need to be beautiful. You can put the stirring rod in. I don't know how you show the hydrate perspective. Good luck. Okay, and I'll leave it there. And then, so again, you can choose to work on this. You can do the worksheet. You can do stuff from yesterday. You can, if you can get on the Wi-Fi or whatever, you want to rewatch the video, that's fine. But you see, it's pretty simple, right? They basically just heated a blue compound and made it white.